Here's a quick recap of the previous video. In the landscape of different types of optimization, QUBO comes under the unconstrained combinatorial optimization. We can delve into QUBO by relating it to a mathematically equivalent and computer science friendly version called the max cut problem by considering this numerical example of a 3-node graph. In general, it can be expressed as a minimization problem in this form. The matrix form, when expanded and simplified, is actually a quadratic expression, and the solution is a binary column matrix. These properties made us come up with the cool acronym QUBO. Then we have the Python code in a Jupyter notebook containing all the mathematical reformulations and implementing the brute force approach to solve the max cut problem. Further, we can generate random problem instances and see how it scales. We concluded that we are guaranteed to find the optimal solution using brute force approach, but very inefficient due to exponential complexity. Now, let's explore alternatives that are efficient in solving QUBO. QUBO solver takes a symmetric matrix Q as input and outputs a binary vector X. QUBO solvers can be broadly classified into exact and heuristic solvers. Brute force is for sure an exact solver for QUBO because we check all possible solutions one by one, whereas heuristic solvers provide an approximate solution. There are classical and quantum algorithms that can provide near-optimal solutions. There are plenty of classical heuristic solvers. Among them, Gurobi and Cplex are considered to be state-of-the-art solvers. In case of quantum, we have quantum annealers and variational quantum algorithms, abbreviated as VQAs. Gurobi is widely used as the classical baseline in benchmarking the performance against quantum algorithms for combinatorial optimization. Since Gurobi is mainly used for empirical analysis, let's directly jump into solving the max cut problem formulated as QUBO. As mentioned in the previous video, in the same GitHub repo, we now have a new Jupyter notebook for Gurobi. With the same libraries installed as mentioned in the notebook containing brute force implementation, we also initialize the same 3-node problem instance and derive the QUBO matrix. gurobipy is the Python library. We install the latest stable version as of today and import them. Then we instantiate a model, add the binary variables, set the QUBO objective, and call the optimize function. We fetch the solution as a binary array and print it along with its objective value. It logs metadata of the execution by default. We can silence it by setting the model parameter output flag to 0. For this small example, we obtain the same solution as that of brute force. Now let's benchmark the runtime by increasing problem sizes. We have the function for generating random graphs, same as the one we used in previous video for benchmarking brute force. Then we create a function that takes the QUBO matrix Q as input. Gurobi solves the problem and returns the solution as binary array and its objective value. Running Gurobi for problem sizes up to 40 nodes, we log and plot the runtimes. We see that it takes significantly more time for certain problem instances. For example, there is this weird behavior where the problem size 38 took more time than 39. Typically, heuristic solvers use branch and bound strategy that relies on mathematical boundaries to prune large portions of the solution space. The bounds are iteratively updated to shrink around the optimal solution and terminates when they converge. But for certain problem instances like these, the branch and bound technique fails to converge the bounds and end up searching massive number of solutions. This means if we generate the problem instances using a different random seed, where the graphs generated now have different edge weights, the problem size 38 takes lesser time than 39. You can also see that the problem size 38 took significantly lesser time than the previous run. In contrast, for a fixed problem size, the runtime of brute force is approximately the same, agnostic to the edge weights. Another thing you have to take into account is that the graphs generated are fully connected. This has a huge impact on the runtime of Gurobi. Sparse graphs correspond to several quadratic coefficients of the QUBO being 0, and this makes it easier for heuristic solvers like Gurobi. Now, running up to 45 nodes, although not as bad as brute force, we notice a trend of also Gurobi starting to have longer runtimes. This is because we are using default configuration of the model parameters. Gurobi's documentation has tips for setting several model parameters, but the one that has the highest impact on the runtime of Gurobi for solving QUBO is the MIP gap. It is the ratio between the upper and the lower bounds and defines the terminating condition of the branch and bound algorithm. By default, the value is set to 0.0001. It has a range of 0 to infinity, so setting an acceptable higher value significantly reduces the runtimes. The most surprising fact is that the quality of the solution is still the same as that of the previous run. But why did it take so long to execute before? As an explanation to this, Gurobi doesn't just run branch and bound algorithm. It uses an ensemble that also include other sophisticated heuristics like taboo search or greedy mountain climbing. We can only guess because Gurobi is a commercial tool and not open source. Gurobi being a state-of-the-art solver, the primal heuristics are specifically designed to guess high-quality solutions. However, heuristic methods do not have the mathematical guarantees and cannot provide a proof. Previously, with a significantly low value set for MIP gap by default, Gurobi's branch and bound algorithm was spending time in proving the optimality of the solution which the other heuristic methods had already guessed. Setting a higher value for MIP gap allows to scale Gurobi for much larger problem instances but without any optimality guarantees. What really makes Gurobi stand out is that the solution it provides, although heuristic, is deterministic. This means that given a problem instance, fixing the model parameters and the hardware you run it on, the algorithmic path of Gurobi remains the same, which implies the solution found also remains consistent with multiple runs. Before we wrap up, there is one key detail. We use Gurobi as classical baseline to scale experiments as far as our computational resources would allow. But Gurobi is a commercial software and restricts running QUBO problems beyond 200 variables. If you are a student or an educator, then you can get Gurobi's license for free. Just Google Gurobi Academic License, click on Claim Your Free License, fill the form, provide your institutional email, and complete the registration process. After sign up, once you log in, you will see a dashboard like this. Click on Licenses on the left. As you see, I already have one license previously created. You can create a new one by going to the request. You should be in the Academic tab. There are several variants. As a prerequisite to this step of generating the license, make sure to be in your institution's network, either use a VPN tunnel or be there physically connected to their network. I usually run the experiments on the same machine, so I have generated a named user academic license. If you want to run the code on a cloud-based platform like Google Colab or GitHub Codespaces, you can go for Web License Service Academic. After you generate, you can click on Licenses on the left. As I said, I have a named user academic license which has to be installed on the computer we intend to run Gurobi. Simply copy this command with the license string, paste it onto the command prompt or terminal and run it. That's it. You will have no licensing limitations. In the next video, we will see a similar way to access D-Wave quantum analysis to solve QUBO problems.